Okay, well, this is a daunting talk to give, not in the least because I have about 10 seconds for every publication she wrote. I'm going to be talking about the science of Anne, but first we're going to start off with part one, where she's an experimentalist. This is a picture of her from the summer of 1977 when I first met her. She was working at SLAC on an experiment with Marty Pearl, and in fact, her first publication was on the excess of E plus E minus and mu plus mu minus pairs in E plus E minus collisions, which could only be explained by the production and decay of the tau lepton, which had been discovered a couple of years before. She actually could have been a great experimentalist, I think. When we were seniors, we did a desktop parity violation experiment together, and she designed all the electronics, and it worked beautifully while I destroyed 6 phototubes by immersing them in helium. So, for discussing her theory, it's really hard to figure out how to organize all these papers. So I sort of came up with this scheme where I talked about some of the major themes in her work, and they overlap a lot. And I'll go through these topics and I'll order the papers chronologically, and you'll see some papers appearing under several different headings because some of them might be supersymmetric and deal with cosmology and deal with neutrinos and so on. And then I'll just feature some highlights. So first of all, flavor and CP violation. So her very first paper was on an SU7 grand unified theory that Howard Georgi gave her. It was on analyzing proton decay operators. But the first paper I put here is one that she did with Anish Manohar and Howard Georgi, where the idea was Howard's, which was to have a large grand unified theory like SO16, I believe, where all the fermions are put into a single spinner, 256-dimensional spinner. So there was a single Yukawa coupling, and then all of the flavor hierarchies and angles and everything came from RG scaling down to the low energy world. So the physics came in from different scales of breaking the symmetries and then the different gauge representations as the SO16 broke down to smaller groups until it finally got to the standard model. And it was a valiant effort. It didn't work too well, but it was an interesting idea, and I'll come back to that a little later when Anne revisited this in a much more sophisticated form later. As you can see, we're starting to flesh out a lot of answers or attempted answers to the questions that Pilar raised, and basically Pilar's talk really was an introduction to all of Anne's work, which was to figure out how physics worked beyond the standard model. So the second thing here are these two papers on spontaneously broken CP and naturally weak CP violation. So this was a paper she wrote in her third year of graduate school, just beginning of third year. And I think this was an outgrowth of her work on this SU7 gut. She noticed this sort of bizarre patterns in mass matrices, and I went back and I looked at this paper yesterday, and I still can't comprehend it. She just looks at these big matrices. She knows that she constructed a model where, let me back up, sorry. So the problem with this strong CP problem is you want to understand why theta bar is less than 10 to the minus 9 experimentally in the low energy world. And of course, if CP was a symmetry, it would naturally be 0. But we're confronted with the fact that we know that there is CP violation in the weak sector. So the question is, how do you build a model where you have the weak CP violation, not the strong CP violation? So a natural thing to suggest is that CP is a good symmetry at high energy. It gets spontaneously broken, and somehow what filters down is just the weak CP violation. The problem with these models is that in almost any random attempt you try, when you go through the spontaneous symmetry breaking scale and you integrate out the heavy particles, you generate finite contributions to theta, which are unacceptably large. So what she found was that there was this model that she could construct where the fermions where CP is spontaneously broken, but when you integrate out all the heavy stuff, you automatically, up to 2 loops, have through 1 loop, you have no contributions to theta. And if you look at the appendix, it's full of these matrices where she says, you can just see that this is the product of 3 such matrices with these properties, and you can see that it won't have any phase in its determinant. And just like GPUs are designed to process graphics, Anne's brain was designed to process matrices. It was just awesome. You could watch her just diagonalize 4x4 matrices in her head. And so this appendix is still mysterious to me. And it was mysterious to almost everybody, but then Steve Barr, who's an assistant professor in Seattle, was able to look through it and try to extract what were the principles that she was using to design this. And this is the sign that she's a graduate student. As an adult physicist, she would have found those rules and would have presented the general way of constructing it, but she wasn't quite there yet. And so Steve Barr did that, and then she used those rules to start generating more interesting models and analyzing them up to two loops in the RG flow. So here's an example of the way she was thinking at the time. In the first paper, this is she talks about this being the dead duck graph as a contribution to two-loop scaling of theta bar, and she doesn't quite have the dry scientific language down yet, and her advisor is the editor, so it got through. So once she had the rules from Steve Barr, she could start looking at the scaling, and so she computed all the two-loop running of theta bar in this model, as well as the finite corrections. And she's able to look at this and just in this general form compute these graphs, and it showed that the theta bar was 10 to the minus 11, which is acceptable and interesting because it's not incredibly small. So she graduated with a thesis basically on those two papers, both of them single-author papers, which is sort of unusual for students of Howard Georgi, most of whom collaborate with Georgi. And Howard very generously said of her that I had many fabulous students who are better than I am at many things, and was the only student I ever had who was better than I am at what I do best. And I learned more from her than she learned from me. So, as a beginning postdoc then, she worked with me on strange condensation, KN condensation in dense matter. We were intrigued by this talk by Igor Klebanov on skyrmions, and he mentioned pion condensation. We said, oh, what's that? And discovered this really cool literature about Bose-Einstein condensation of pions in nuclear matter that originated in Russia in the early 70s. It didn't work very well because pions have a p-wave attraction but s-wave repulsion to nuclear matter. So we started looking at kaons because we had just learned about chiral perturbation theory from our advisor. And we found, well, both the s and p-wave were attractive. So maybe even though the kaon is heavier, this might be interesting. We convinced ourselves that it was a huge effect and then discovered we'd made a mistake. We were depressed. And then the next day, there happened to be a talk by Donahue about the pion-nucleon sigma term, and then we realized, my God, there's an operator no one's been putting in the chiral Lagrangian because it's SU3s. It involves the quark mass matrix, but it's SU3 symmetric, so people find it boring. We put it in, and it looked like maybe KN condensation could occur then, so we had a lot of fun writing that up and thinking about what went on inside neutron stars. So she was, as she got to know more about the strong interaction, she got very intrigued at the idea that there could be interesting physics hiding right underneath our noses in the complicated hadron spectrum. So this is just examples of a few of some of the early papers she wrote, but it's a theme that she came back to again and again, that there might be interesting new physics right in the hadron spectrum. And even her last paper, which I'll talk about, talks about maybe baryogenesis happening in the B meson system. So moving on, 1993 to 2011, again, lots and lots of papers on flavor, on CP violation. I'm going to mention this paper here, Suppressing Flavor Anarchy, because it goes back to that first paper that I mentioned, which was Flavor Democracy. I guess we're taking a tour of various political theories here. This one was written with Matt Strassler, and it was extremely clever. The idea was to couple the standard model to some conformal sectors. And the idea then was that the problem with the RG scaling explaining all of flavor from the original paper is that when you get logarithmic scaling, there's just so much you can do. You can't get really huge hierarchies from logarithmic scaling typically. But here, if you couple the standard model to all these bizarre particles with conformal, which transform non-trivially under those conformal groups, these SP8s, then the scaling can be power law, and the amount of scaling you get has to do with the anomalous dimension of the operators. And with the development of all the tools that Nadia Seiberg gave us with supersymmetric theories, you could do these sorts of calculations in a reliable way and know what you're doing. So these types of models look very complex, and it didn't bother Anne at all that you're storing in all sorts of particles that hadn't been seen, because the whole point was for her to do a model was to try to understand what was possible, what sort of mechanism existed. And so here's a nice quote from a postdoc who worked with her recently, Chanda. Anne told me that to be happy as a model builder in particle physics, I had to be okay with something like mounting a moose head on the wall and putting a purple scarf on it, not worrying about why I was wearing a purple scarf. This might actually be Anne pretending to be a moose, I'm not sure. Finally, more on the flavor and strong CP section, in recent years, she got very interested in this baryogenesis from heavy flavor. I will return to this a little later on that topic. Neutrinos. So neutrinos became, she got fascinated with them. She got very interested in this experimental evidence that later went away for a 17 keV neutrino and wrote several papers on that. The ones I'm going to mention, I think these two papers here on mass-varying neutrinos were lovely pieces of work. So the idea here was to address all these strange coincidences, cosmological coincidences, and the fact that the CDM and the baryon energy and the neutrino energy and the radiation energy and the cosmological constant all tend to be sort of clustered in the same order of magnitude today, while if you, at about a redshift 1,000, and very strange that they come together so close like that. And so this coincidence is something she wanted to talk about. They proposed this rather strange theory where you introduce a very light scalar with a potential that is dependent on the local neutrino density. So this sort of takes the ideas of MSW, that there could be medium-dependent physics, and really takes it to an extreme. So you have an ultralight particle that can react quite significantly to the presence of neutrinos. And as a result, you can make the properties of neutrinos change radically in different regimes. The order of merit here is this number r. If it's greater than or equal to 1, it means that neutrino mass parameters are modified. So in the regions where we have quite a bit of data, the solar core, reactor cores, and beams, you see there's very little modification at all, because it's in a region where there's not a very high density of neutrinos. But once you start going into supernovas or during the Big Bang nucleosynthesis, you find a very large value of r. And what happens then is that the density of neutrinos distorts this potential and completely changes the mass matrix of the neutrinos. So they call these mavens, mass-varying neutrinos. Maven is an English word for somebody who's a real expert in something. So Anne always liked doing word plays in her papers. So Neil, who was a collaborator on that, stressed that when you look at these papers, you should think about how much fun it was to write them. That when he collaborated with her, fun was really a big part of collaborating. And they loved making up names for particles. That Maven paper, another paper they wrote on supersymmetry breaking, they have these new scalar particles that they call bachelors, and they were joking that their supersymmetric partners should be spinsters, and so on. So she went on and later went back to that and talked about how these mass-varying neutrinos could change the CMB as well. So it was a theme that went through quite a bit of her work. Supersymmetry. So Anne was not so much seduced by supersymmetry in the 80s when a lot of people were working on the MSSM, but she became especially interested in supersymmetry after Seiberg's papers. However, before that happened, there is one foray into supersymmetry that had quite a big impact that she made, which was we had been working together on electroweak baryogenesis, which I'll be mentioning a little later, she and Andy Cohen, our joint collaborator, wrote the first paper, I think, on using electroweak baryogenesis within the context of supersymmetry, where the attraction of supersymmetry was that it was easy to extend this MSSM with scalar sector and make much stronger first-order phase transitions. And so that was the first attempt, and then she returned with Patrick Huet sometime later and gave a much more sophisticated analysis of what's going on. But then once the Seiberg papers came out, she became fascinated with supersymmetry, in particular the dynamical supersymmetry breaking aspects. And so she wrote the series of papers with Michael Dine and Yuri Sherman and Yossi Nir in different combinations, where she harnessed this dynamical supersymmetry breaking to come up with a completely new paradigm for why we don't see supersymmetry in the low energy world. At the time, it was almost a religion, the minimal Sugra model, where you had a hidden sector that communicated via gravity, and it was a very strong dogma, but had a lot of problems with it. So here's one of the papers that they wrote. These are very highly cited. The problem, as I said, was you had this dogma of the old Sugra breaking, and it had a number of issues. One is that it suffered from very light gauginos. There were all sorts of assumptions built in about flavor. And I can attest that the mindset was very strange. I gave a talk in 1995 at SUSY 95, and I talked about the SUSY flavor problem. And the podium got mobbed after my talk by people telling me that I was nuts, there was no flavor problem. It was strange. I really didn't like it. It was such a groupthink at the time that everything had been solved. And really what the problem was is that you put in all these operators suppressed by powers of M Planck, you make them flavor symmetric so that the squarks are all degenerate. And then you say that all the flavor structure of the standard model comes from somewhere. But it's all hidden up at the gravity scale. So you don't know how in the world can this new physics create all the flavor structure in the visible world, yet make all the squarks degenerate. And so it wasn't actually part of the model. It was just an assumption. Furthermore, so the problem with light gauginos is typically it was difficult to make the hidden sector operators be low dimensional. So all the gauginos would get their masses from higher dimension operators and be very light. There were big gauge groups that you had to worry about asymptotic freedom below the Planck scale and so on. So Anne wrote a very nice review of dynamical supersymmetry breaking in '97, and she points out what the virtues of this were. The theory contains gauge singlets, and therefore it's very easy to make hidden sector models with gauge genome masses that aren't too light. You don't have to have chiral fermions under the gauge group, chiral superfields. And so it's possible to, this is a technical thing that makes it easier to design the models. You can have large unbroken global symmetries, allows you to put the standard model interactions in it. You can have classical flat directions lifted by quantum effects, which is an important condition to have quarks and leptons participate in the supersymmetry dynamics. And it's easy to make a theory with multiple scales, which is useful, and you don't have problems with this U1R invariance, which tends to lead to R axions, for example, that are cosmologically bad. And these papers that she wrote then were really the foundation, not just for gauge mediation, which is what they introduced in these papers, but also gauge genome mediation, which was started by two simultaneous papers, one involving her, anomaly mediation by Randall Sundram, new solutions to the mu problem, the whole idea of gravitino dark matter. So it's really a foundational body of work that changed the way people think about supersymmetry in the real world. And this really goes to show one thing about physics is that when somebody has a really great idea, it doesn't mean that there's one fewer great ideas for the rest of us. Quite the contrary, it's like opening a door and opening up a whole new territory for everybody to explore. And so one sign of that is if you look at the papers that cite her paper, among them are many papers with 500 or 1,000 citations themselves, because they have gone off into this new territory and found all sorts of interesting things. The next foray into supersymmetry is a project I did with her and Andy Cohen, which is the more minimal supersymmetric standard model. It had been observed that a lot of the fine-tuning problems and the electric dipole moment problems and so on in supersymmetry were associated with the lightest two families. And so we took a lot of that information that was floating out there and codified it into a sort of a coherent framework about how you could have the supersymmetric particles of the first two families be at a much higher scale, like 20, 30 TeV or something, while only the third family, which was necessary for naturalness, or even parts of the third family, down at the TeV scale, and that this would make supersymmetry still solve naturalness problems in the standard model, while being much more compatible with the experimental results. And this has gone on and has various forms now. I think it's called natural supersymmetry in some of its more modern guises and so on. And then she went on to, we both looked at B-factory physics from this theory, and she went on and did some work on CP and flavor violation. Lots of papers on supersymmetry. I'm going to focus on this one here, Dirac gauge genomasses and supersoft supersymmetry breaking, because again, it's one of these really creative, funky papers that she just sort of would generate. This one, the idea was to say that the gauge sector actually doesn't have n equals 1 supersymmetry, but has n equals 2 supersymmetry. This is sort of taking, supersymmetry was this beautiful idea throughout the 70s that nobody quite knew what to do with until there was this very transformational paper by Witten who pointed out that we should love supersymmetry because it solves quadratic divergences. And Anne took this a little bit further with her collaborators here, which is that you can even soften the divergences further by putting in a little bit of n equals 2 supersymmetry. Now, n equals 2 for the whole world is a terrible idea. It's really hard to get anything that looks like the real world in n equals 2, but the gauge sector could be n equals 2. It's broken through connections to the matter fields, which are in n equals 1 chiral multiplets, but the result is much softer supersymmetry breaking appears from that. So the super partners obtain masses which are simultaneously consistent with experiment and natural electroweak symmetry breaking. They predict the sign of, you get finite calculable corrections to scalar mass squareds. You can solve the mu and b mu problems. You can avoid flavor changer neutral currents. You can avoid CP violation, and so on. So this sort of theory solves a lot of problems, and it's sort of, again, out of the box type of thinking about symmetries. So let me move on to compositeness. I thought this was the appropriate picture for that. So one of the things I have received a lot of lately are emails from people, and a lot of them from women some even who never met Anne, who said that she was a really big effect on their lives, partly just by being an example of a woman scientist who can be at the top of the game and have a normal life and have a family. And I even just heard a story last week from a young physicist who got her PhD in Australia. And while she was a graduate student, this male physicist told her that if she was planning on having a family, she shouldn't go into physics because you couldn't do both. And she denied that. And this guy said, well, name somebody who succeeded. And so she said, Anne. And then she wrote to Anne and told Anne about the story. She'd never met Anne, and apparently Anne emailed back to her, encouraging her to stay into physics, and then wrote a note to the guy, told him he was a jerk. But she was very nervous about children causing harm to her career. We waited until after we both had tenure at age 35, so we wouldn't end up in different cities. And then she made me sort of promise in blood that I'd be a participatory father, even though you'd think that after knowing me, being together for 16 years, she'd have some idea. But so, compositeness, littlest Higgs. This is a paper that she wrote with Nima and Andy and Ami Katz. So Georgi and Arkani Ahmed and Cohen had been writing these really cool papers on the dimensional deconstruction, and they had this model of electroweak symmetry breaking that was very weird, where basically you could imagine this being an extra dimension, and you're breaking electroweak symmetry by having a Wilson line around the extra dimension. But they've discretized it, so they now have a finite number of groups. So instead of thinking of the extra dimension as a physical dimension, you can think of it as a dimension in model space, different gauge groups connected to each other. And it was a little obscure why exactly it was working. And by the accounts of the authors of the paper, it was really Anne who boiled it down to what exactly was the essence of this model that made it work, and how do you make it as small as possible? And so they came up with this theory here. And the idea was, so the idea that they noticed is that you could make you marry the composite, well, the idea that the Higgs is a Goldstone boson to gauge theory where you have two SU2 cross U1 groups, where the theory is designed so that if one of them wasn't gauged, then the Higgs would be an exact Goldstone boson. And therefore, you need both gauge couplings involved in order to generate a potential for the Higgs. And so rather than the Higgs getting all of its mass squared and potential proportional to G squared, it comes in at G squared, G prime squared, and it's smaller. And this is exactly the physics that was going on with their chain, where the more groups you have in this chain that are required to participate together to give the Higgs potential, the more natural or the smaller the Higgs potential is compared to the UV scale. Then there was a very large body of work that I participated with, and for a good part of this is electroweak baryogenesis. So again, there was a dogma, a widely accepted picture that baryogenesis came from grand unification. It had all the ingredients right there. It had baryon violation, it had out of equilibrium physics because it's so close to the Planck scale. It's easy to put in CP violation. It had various problems. It was hard to make it compatible with inflation. It had various other issues. But when Rupikov, Kuzmin, and Shpashnikov came out with their paper in '85 that the electroweak baryon violation that Atoft had discovered in the 70s and had discovered to be extraordinarily small was in fact large and active at finite temperature. And so this was out there, and people didn't know quite what to do with it for years. I think Yanagita's paper on leptogenesis was one of the early ones, which was very creative. But in terms of turning it into baryogenesis, it took a long time to put it together with the idea that the electroweak phase transition could also be the source for out of equilibrium physics. And so the idea then was first order phase transition, bubbles, pushing stuff around, and that was what we introduced in this series of papers, where the source of CP violation could either be in the neutrino sector or in the tops, or in the Higgs sector, and so on. So lots of different, very complicated physics during a first order phase transition. You know, we discovered them sequentially. Oh yeah, we forgot about diffusion. Oh yeah, we forgot about device graining. So a bunch of things ended up going in there. And then, as I mentioned before, that Anne took this further and put it into the supersymmetric context. And she ended up getting the Sakurai Prize for her many contributions to baryogenesis, among other things, but her talk was about baryogenesis. So then, here's a bizarre paper that we wrote together with Andy later. We decided, there's all this stuff about holography, and we got very confused about it. How do we marry gravity with field theory? It's an old problem. And we decided, why don't we just be super dumb and say, let's take quantum field theory and push it as far as we can without ever having to mention gravity. How far can we push it? And so the idea was we have a box of a certain size, we have a lattice of a certain lattice spacing, and we're going to do quantum field theory on this system. But the rule is that you're not allowed to have any configuration there that requires gravity. Well, that puts severe constraints on the size of the box relative to this coupling, because the maximum energy state, where you populate every state to its highest energy state inside this box, has to have a Schwarzschild radius which is bigger than the box, otherwise you're going to have to talk about gravity. And what was attractive about this picture is if you make the box the size of our horizon, you automatically get an energy density which is on the order of the observed cosmological constant. So, but that's just sort of hand wavy. Anybody could have done that back of the envelope calculation. It is a more extreme IR-UV correspondence than, say, holography gives you. But the interesting question then is, are there any consequences by having this constraint? And so you do physics in this box, and you find, well, you've got an IR cutoff and you've got a UV cutoff, and there's a relation between them, but there's some effects that deviate from the field theory you learn in grad school because of these cutoffs, and there's a constraint on it that you can't get rid of. And so, for example, we computed G-2 for the electron in this box, and we minimized the new physics that comes from these cutoffs, and found that the effect of the cutoffs was larger than the top, about twice as big as the top quark contribution to G-2 for the electron. So that's out there. It still intrigues me. I don't know whether it means anything or not, but it was fun. So Anne got extremely interested in dark matter. Lots of papers on dark matter, lots of papers on new ways to have dark matter annihilation with long-lived particles, constraints on dark particles from neutron stars and from gravitational waves. Her last series of papers were really focused on this interesting idea that baryogenesis could come about because of CP violation in the B meson sector. This is amazingly creative. This, again, is just, throw away all of your preconceived notions about baryogenesis and say it's right under our nose. So, Mezzino oscillations, charmed or beautiful baryon oscillations, and then the last few papers there, all on B mesons and baryogenesis coming from this sector here. So this is her last paper. It was put out in July and then just revised slightly recently. Gonzalo will give a poster on this on Thursday. But just to give you an idea, I mean, this is really a cool paper because it puts together so many of Anne's interests. It's got supersymmetry, it's got baryogenesis, it's got neutrino physics, it's got dark matter, it has heavy flavor in it. It's got all sorts of strange things. It's got B mesons are making baryons at MeV temperatures, as low as you can get, and still get away with nucleosynthesis. It's got CP violating oscillations that decay into a dark sector, so it produces your dark matter. The dark matter, and of course, very important to Anne was why do a model that's not testable? So all of these series of predictions for B factories and hadron colliders, novel long-lived particle searches, and so on. So I just want to end with a quote from John Preskill. Thank you.